So the next lecture in the energy and momentum unit is on conservation of momentum, and we're going to look at conservation of momentum in one dimension first, because these are easier problems than when we look at it in two dimensions. In later years, when you study conservation of momentum, you'll look at it in three dimensions as well. But for the purposes of this course, we have to do one dimension and two dimensions. This is section 5.2 in your textbook, so if you want to follow along, you can look at it there. We've talked about momentum. It's called a quantity of motion, is how Newton referred to it. And it is the product of the mass times the velocity of an object that is moving. If an object is not moving, of course, its velocity is zero, so it has a zero momentum. So this slide here says when a cue ball hits an 8-ball in billiards, the 8-ball hits the cue ball. So there's the force of the cue ball on the 8-ball, there's a responsive force from the 8-ball to the cue ball. So both objects hit each other, even though one was stationary. So in a collision, two objects exert forces on each other. And one way of analyzing the motion of these objects after the collision is to analyze their momentum before the collision and their momentum after the collision. So the momentum is going to be conserved. So if we look at this, this is the algebraic proof of that. So if we look at this, we have the object A, which is a mass that's labeled MA, and object B, which is a mass labeled MB. Because of Newton's third law that every force has an equal and opposite reaction, so the F action is equal to negative F reaction. What we would have is the force on A is equal to minus the force on B. So if we change these to momentum, now remember momentum can be found as mv, or it could also be force times time. So if we have Fa times delta t equals minus Fb times delta t, the delta t is shared, the shared time for both sides of that equation of the collision. And if we then rewrite that as that delta t into a tf and a ti, so a final time and an initial time, we can rewrite the equation as mv for A, where v is the final position, minus mv for A with the initial velocity, and that would be equal to the negative of mbvbf minus mbvbi. So rearranging this equation to get rid of the negatives on both sides of the equation, you move the negative mavi to the right side and move the negative mbvbf to the left side. Rearranging, we end up getting mavai plus mbvbi equals mavf plus mbvf. So one thing you might notice, all of our initial conditions are on the left side of the equation. All of our final conditions are on the right side of the equation. So this gets us to the conservation of momentum law, or equation for the law, and that is that the rho initial equals the rho final. So the momentum before is equal to the momentum after. That's the law of conservation of momentum. Sometimes we write this, instead of i's and f's, we write this with a prime instead. So that prime that you see indicates that this is an after condition. So it's our VA before is just VA, and our VA prime is our velocity after of object A. Now, momentum is a vector quantity, but what's interesting about this is that the momentum is conserved in each dimension independently. So the momentum in the x direction has to be the same in both the initial and final conditions, and the momentum in the y direction has to be the same in both the initial and final conditions. When we get into conservation of momentum in 2 dimensions, this is an important property. So I'd like to copy down what's in green. It says law of conservation of momentum. When 2 or more objects collide, the collision does not change the total momentum of the 2 objects. Whatever momentum is lost by one object in the collision is gained by the other. And the total momentum of the system is conserved. And now this note's interesting because it says there's 2 general categories of interactions. So we have collisions or explosions. A collision is what we've been talking about mostly, where 2 objects kind of hit each other. An explosion typically can be thought of as an object with a momentum of 0 because it's not moving before the explosion. Afterwards, the individual pieces of the object after the explosion have separate momentums. But the sum of the momentums, if we add them using the vectors, will be 0. So that's an interesting aspect of that as well. Copy this down as well, law of conservation of momentum. This describes basically what I said previously in very succinct words. So you might want to pause the lecture and copy that. So it says here, in reality, systems are rarely perfectly isolated. In nearly all real situations, immediately after collision, frictional forces and interactions with objects change the momentum of the objects involved in the collision. So just to comment on that, now we talk about conservation of momentum. We've been talking about it where we have a collision and we say what's the situation afterwards. In reality, it depends on when we actually make that calculation, because while there's conservation of momentum, there's a lot of other forces to consider, and frictional forces are one of the main ones. So this may make it look that the law of conservation of momentum is not very useful, since as soon as friction gets introduced, it's difficult to find out what our final velocity will actually be after the collision. But one thing that's important to note is that if we look at this in that very small time that the collision's happening, that delta t, and we look at the velocity before at the start of that delta t and the velocity after at the end of that delta t, the law of conservation of momentum is consistent during that time because friction has not yet acted on either object. So if you know the conditions just before a collision, you can always use the conservation of momentum to determine the momentum and thus the velocity of an object at the instant after a collision. So sometimes those are the only values you need to know to solve a problem. Now, when you get to the tests and quizzes later on in this unit, you'll have to make a decision on whether to use the conservation of momentum to solve some problems, because it might not be the case that you can use it, depending on if friction might be introduced in these problems, depending on when you need to find out your final velocity. So in the one-dimensional collisions, each vector only points in one of 2 ways. They're either going left or right or up or down. It's best to choose your positive based on, I suppose, it's your decision, but choose it whatever way would make it convenient for solving the particular problem. So oftentimes we assign right as positive, left as negative, up as positive, down as negative. But if we're talking about something that maybe is involving the force of gravity going down, you might want to use down as positive. Just whatever decision you make and however you present your problems, if you're writing them as vectors, or when you write your answers as a vector, make sure that you include the direction, unless it's obvious that you are you're choosing a convention in a way that that wouldn't necessarily need you to show the direction. So if your positive is obvious that it's going to be moving to the right, then you can just omit that direction. So here's a problem that says that we have a 1,750 kilogram boxcar rolling down a track towards a stationary 2,000 kilogram boxcar, and these two boxcars collide and they stick together and then they kind of move on. We're asked to find the final velocity of both of the objects, both the boxcars, because they're stuck together in the final position. So we also have our velocity before. It's 5.45 meters per second. And we can say moving to the right is positive. We can call it moving to the east. So I'll show you how to solve this very shortly. So for this problem, our givens are the mass of A, the mass of B, the velocity of A, and we need to find the velocity of AB prime. Now the velocity of B is 0. I'm not going to bother writing that, but we'll get into that shortly and show you how that works. What I would also like to say is that this problem would be one where we don't necessarily have to state the direction for our final answer, because our velocity was given in a picture with an arrow pointing to the right, and it was given as positive. So that implies that if our answer is positive, we're going to the right. If our answer is negative, we're going to the left. So to start this off, we know that our momentum before, so our rho is equal to our rho prime. So momentum before is equal to momentum afterwards. Momentum before is MA VA plus MB VB. Our momentum after, the A and the B get combined together to an MAB, and we have a VAB, which is just basically VAB prime in this case because it's happening after. This MAB, though, just so that you're aware, MAB is actually a sum of MA plus MB. So, looking back at this, we know our VB is 0. So if our VB is 0, this entire term will be taken away. We also know that, or actually in this case now we can, every other value is known, so we can isolate for VAB, and I prefer that you isolate these before you start subbing in values to solve them. It actually makes it much easier to do in terms of writing it into your calculator, and I find that students make less errors if they isolate first. So we have VAB prime is what I need to isolate for. It's equal to, VA MA over MAB. So this equals VAB prime equals MAVA over MAB. And that becomes, I can substitute now 1750. My VA is 5.45 over 1750 plus 2000. That's my MAB. And writing this into the calculator, I end up with 1750 times 5.45 divided by bracket 1750 plus 2000, close the bracket, equals 2.543, or I'm going to write that as 2.5 meters per second. That's my solution. It's two significant digits. Because we're limited, so here we have three significant digits. We have the 1, the 7, and the 5. Here we have 3. We have the 5, the 4, and the 5. Here we have 2. Because we're not told anything otherwise, so we have to assume two significant digits for this this value. It's not 3 because we're not sure how much this has been measured. It looks more like an estimate of 2,000. So that's our limiting factor in terms of significant digits, so we have to go with 2. All right, next question that we can look at involves an object, a head-on collision with two objects that are moving. So in this case we have M1 That's 2.5 kilograms. We have M2, that is 7.5 kilograms. We have a V1, that is 6 meters per second. And we have a V2, that is negative 15 meters per second. So here's a question where we don't necessarily need to write the direction in terms of east, west, north or south or anything of that nature, or left or right. We can use the convention that's given to us in the question that right is positive, left is negative. We don't even need to really state it. And it says in the second part of this, or when I actually read this question, everything I got was from the image. It says in the question, if the 7.5 kilogram object has a velocity of negative 4.5 meters per second after, what is the velocity of the first object after the collision? So looking at our paper here, sorry, I'm just going to move this up, we end up seeing that our with all of our givens, the only thing that we need to solve for is this VI, or V1 prime, and our momentum before is equal to our momentum after. Our M1 V1 plus our M2 V2 is equal to our M1 V1 prime plus our M2 V2 prime. None of these values are 0. So we have to rearrange based on, we have to rearrange for V1 prime. So our V1 prime is going to be basically this term here, or these two terms, subtract this term, divided by M1. So I'm going to write 1 over M1, and then I have M1 V1 plus M2 V2 minus M2 V2 prime. I can expand this in. So V1 prime equals V1 plus M2 over M1. And this is going to be the same term for both. And it'll be V2 minus V2 prime. Now I can do my substitutions. V1 prime is equal to 6.0 plus M2, which is 7.5, over M1, which is 2.5, times V2, which is minus 15 to start, minus V2 prime, which is minus 4.5. So V1 prime, I can do this calculation here. It is 6 plus 7.5 over 2.5, which is 3, times bracket negative 15 minus 4.5, which is negative, close the bracket, I hit equals, I end up with negative 25.5 meters per second. Looking back at the problem here on these givens, I have two significant digits, 2, 2, and 2. So my solution here has to have 2. Negative 26 meters per second is my answer. Let's do another one of these. So here's a recoil reaction. This is similar to an explosion type reaction. And in this case, what we're going to have is we have our object is not moving initially, I believe. So let me read this first. It says that we have a 1,400 kilogram cannon, and there's a that includes the 50 kilogram ball with the cannon. So that's our mass before. And it fires this cannonball and it gives it a velocity of 50 meters per second north. So what is the initial velocity of the cannon the instant after it fires the cannonball? And we've labeled, you can see that the masses are labeled as MB for the ball, MA for the cannon. So what I'm going to do I'm just going to write down my givens with, I'm going to separate it because our MA is really 13,050 kilograms and our MB is 50 kilograms. And our initial VAB is 0 meters per second. And our final VA we need to find, but our final VB, we actually know that it's 50 meters per second north. So I'll show you what I wrote here for this problem. Now, my momentum before has to equal my momentum after. My momentum before in this case is MAB VAB. My momentum after is MA VA prime MB VB prime. My VAB is 0. So this entire term is 0. So this becomes 0 equals MAVA prime plus MB VB prime. I need to isolate for VA. So my VA prime is equal to negative MB VB prime over MA. Now I can substitute. So VA prime is equal to negative MB, which is 50, over MA, which is 1350, and VB prime, which is 50. This is to the north direction. So I end up with 50 times 50 divided by 1350. I have 1.8. That's going to be negative. But, so let me write this down. VA prime equals negative 1.852, and that's going to be going to the north direction. I need to, convention is to write this positively, so I'm going to flip this to south and get rid of the negative. So VA prime, and I'm going to round it to, back here it looks like I have a limit of 2 significant digits. So I'm going to round it to 1.9 meters per second south. And that's my solution here. So that's it for this lecture. Next one's going to be when we look at a bit more complicated, which is in 2 dimensions.